So in this video, we will talk about the cracking of alkanes. We will see some chemical equations of different examples of cracking reactions, and then we will discuss why short chain alkanes are more useful than the longer chain ones. And finally, we will see the types of cracking, which are thermal and catalytic. Basically, cracking is the decomposition or breaking down of long chain alkanes into shorter chain alkanes and alkenes which are more useful. For example, we have octane, C8H18. Now, upon cracking, we may get hexane, C6H14, and C2H4, which is ethene. Now, this is a typical cracking reaction where you're cracking a longer chain alkane, you're getting a shorter chain alkane and an alkene. Now, the reason why we're doing this is because hexane is more useful as a fuel. We will dig deeper into this later on in the video. And our second product is ethene. Now, it is a very common alkene. If you polymerize ethene, you'll get polyethene, which obviously has some very common industrial uses. So sometimes your alkane will have a very long carbon chain. Let's take decane for simplicity, C10H22. It is usually longer than that. It has more than 10 carbons in its chain. So decane upon cracking, this might give you more than two products. One of them will definitely be a short chain alkane, C5H12, which is pentane. But instead of one alkene, you'll get two alkenes as your product. So C3H6, propene, and C2H4, which is ethene. Keep that in mind. Now, sometimes your starting alkane will already be very short chain. For example, if your starting alkane is propane, then upon cracking, you will not get any more alkanes. You will get an alkene in the form of propene here, and you will get hydrogen as your other product. And you'll get a hydrogen molecule as your other product. Now you might be wondering why these shorter chain alkanes are more useful than the longer chain ones. That's because these shorter chain alkanes are more flammable than the longer chain ones. Now you might remember I've told you that these alkanes are mostly used as fuels. Now if a substance is more flammable, that means it is more efficient as a fuel. So that means the shorter chain alkanes are better fuels than the longer chain ones. Now if you want to dig in deeper and know why these shorter chain alkanes are more flammable, it's because they have a higher CH bond is to C single bond C ratio compared to the longer chain alkanes, which have a lower C single bond H to C single bond C ratio. Now to illustrate the difference between the C single bond H to C single bond C ratios, let's compare two very simple alkanes, ethane and propane. So in ethane, we have one C single bond C here. So let's put one here. And how many C single bond H do we have? 1, 2, 3, 4, 5, and 6. So we have 6 C single bond H. Now, on the other hand, in propane, which is a longer chain alkane compared to ethane, we have 2 C single bond C, so that's 2, and we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 C single bond H. Now if you simplify this ratio here, you can simplify it to 4:1 in its final form, whereas this one here will just be 6:1. So which ratio is higher? The ratio for ethane is higher than the ratio of propane. So this proves that short chain alkanes are more flammable and as a result more useful than the longer chain ones. Now let's look at the two types of cracking, thermal and catalytic. The differences between thermal and catalytic cracking are in the conditions that are used. So in thermal cracking, we use a temperature of around 700 to up to 1000 degrees Celsius. Whereas in catalytic cracking, the temperature is much lower, around 500 degrees Celsius. With regards to pressure, in thermal cracking, we use around 70 atmospheres, and in catalytic cracking, it's just only 20 atmospheres. Now, as you might have guessed, in thermal cracking, no catalyst is used. Whereas in catalytic cracking, we do use a catalyst. It's zeolite. It is a catalyst which usually contains aluminium oxide and some silica as well, SiO2. Now, this zeolite here, as a catalyst, it reduces the activation energy for the reaction, which is basically the minimum energy that is needed to initiate a chemical reaction. So as the activation energy is reduced in catalytic cracking, the lower temperatures and the lower pressures compared to thermal cracking is sufficient to carry out the reaction.